Assalamualaikum and hi, we are from Group 15 going to present our final project design. This is Aquanova organization chart. So we have Haja as operation manager, and we have Haja as an engineer, and we have Linda as a technician, and also Aisha as a co-technician. Okay, next, this is our presentation outline. As a for the presentation outline, we're going to present about introduction, problem statement, objective, methods, result and discussion, conclusion, entrepreneurial opportunities, and reference. Our introduction is wastewater treatment plant play a vital role in protecting public health and represent river water quality by treating wastewater prior to the discharge. As we know that wastewater treatment plant function as a pollution control system that prevent harmful substances from the entering natural waters body. If released without treatment, this pollutant can contaminate river, harmful aquatic life, and pose health risk to human. In the Langat area, rapid urban development and population growth have resulted in increasing domestic wastewater generation, which pose a potential threat to the quality of Sungai Langat if not properly treated. The Langat area has undergone rapid urban development, including residential and commercial expansion. So, without an effective wastewater treatment system, this increased wastewater load can negatively affect the quality of Sungai Langat, which is an important river for surrounding communities and ecosystems. So this project focuses on the design of wastewater treatment plant in Langat to effectively treat wastewater before discharge into the reservoir water body. So this project is a design based on study that focuses on developing and operates wastewater treatment system rather than operating an existing plant. The design involves selecting suitable treatment units and processing to ensure effective pollutant removal. Lastly, is the proposed design aims to comply with Malaysian Advanced Discharge Standard while supporting sustainable wastewater management and environmental protection. Because the proposed wastewater treatment plant is designed to meet the influent discharge standards set by Malaysian environment authorities. And then the compliance with this standard ensure that pollutant level in the treated effluent remain within acceptable limits.
I will be presenting the problem statement and objective of our project on the Langat wastewater treatment plant. The problem statement is the rapid urbanization and population growth in areas served by the Langat wastewater treatment plant have significantly increased the volume of municipal wastewater generated daily. Wastewater for resident, commercial and institutional areas contain pollutants such as organic matter, suspended solid, nutrient and harmful microorganisms. The second one is impact if untreated. If this wastewater is discharged without proper treatment, it can lead to serious environmental issues, including water pollution, unpleasant odor, and the spread of waterborne disease. River, lake, and surrounding ecosystem may also be negative effect which can harm aquatic life and reduce water quality. Moreover, existing wastewater treatment system may face challenge in handling higher flow rate and strong wastewater characteristics, which can reduce treatment efficiency in the system is not properly designed or upgraded. Inefficient treatment can lead to higher operation costs, poor effluent quality, and non-compliance with environmental regulation. This highlights the importance of developing a well-engineering and adequate size wastewater treatment system. The Langat wastewater treatment plant serves as a reference for this project because it represents a typical municipal wastewater system and provide a practical case study for design and analysis. The first objective is to design the unit operation at the Langat wastewater treatment plant for treating municipal wastewater into environmentally safe effluent. This objective is crucial because it ensures that the treatment system protects the environment and operates safely under the aspect wastewater flow and characteristics. The second objective is to draw the layout and process design of the treatment unit using AutoCAD. Based on the design unit operation, this allows us to visualize the treatment process, plan the arrangement of unit logically, and ensure that the system is practical, efficient, and technically feasible for implementation. The third objective is to calculate the wastewater equality parameter, including the biochemical oxygen demand and totally suspended solid of raw and treated wastewater using Microsoft Excel. This is important to evaluate the treatment efficiency of the process system and ensure compliance with the environmental quality sewage regulation, demonstrating that the design meets both technical and regulatory standards.
Next, methodology. A flowchart of work. We began our project with the introduction and preliminary study in the first week. During this stage, we clearly defined the objective and scope of our project to ensure we had a focused approach. We also assigned roles and responsibilities among our team members to streamline the workflow and ensure efficient collaboration. Site selection and data collection. In week 3 to 5, we focus on the site selection and data collection. We select Langat Wastewater Treatment Plant as our study site. Key data were collected, including the population equivalent of 11487.03 and the per capita wastewater flow of 2 to 5 liters per day. This data form the foundation for our design calculation and analysis. Third, literature review and data analysis. From week 6 to 9, we conduct a literature review and data analysis. We refer to Malaysian standard from IWK, DOE and MSIG to ensure our methodology is compliant and accurate. We also analyze the basic wastewater treatment data to answer treatment, understand treatment process and identify the design requirement for our project. Next part, calculation and detailed design. In week 10 to 12, we perform calculation and detailed design. This included the design of the sewage system, primary treatment, and secondary treatment units. We also prepare technical drawing using AutoCAD, ensuring that all design specifications and standards properly documented. Last one, final report and presentation. In week 13, we compiled the final report and prepare our presentation. This step involves summarize our findings, verify our timeline, and ensure that our report clearly communicated the methodology and result of our project. Today, we are presenting the outcome of this. I will explain the schematic design of the Langat Wastewater Treatment Plant. Our design follows the standard treatment sequence, starting from the sewer system and ending with the treated effluents. The primary treatment stage is highlighted in blue. It includes the first process that remove large and stable solid from the wastewater. First one, sewage system. Collect wastewater from residential and commercial area. Second, pumping station. Move wastewater to the treatment facility efficiently. Third, screening. Remove debris such as plastic, rag, and other large objects. 4. Grid chamber. Steal out sand, grit, and small stone that can damage equipment. Primary sedimentation tank allows suspended solid to settle by gravity, reduce the solid load for the next stage. First, sewage system. Collect wastewater from residential and commercial area. Second, pumping station. Move wastewater to the treatment facility efficiently. Third, screening. Remove debris such as plastic, rag, and other large objects. 4. Grid chamber. Settle out sand, grit, and small stone that can damage equipment. 5. Primary sedimentation tank. Allow suspended solid to settle by gravity, reducing the solid load for the next stage. The secondary treatment stage is highlighted in green and focus on removing dissolvent and suspended organic matter biologically. First, aeration tank. Wastewater is treated biologically where micro breakdown organic pollutant. Second, filtration and disinfection. Remove remaining solid and pathogen to ensure the effluents meet safety standard. Last one, treated effluents. The clean water is discharged safely into the Langat River. For C, design basis and assumption, population is 11487.03, cubic 9304 meters square per day, water demand 2 to 5 liters per capita days. D, software and source. First, AutoCAD. Second, Excel. Third, Google Maps. Last one is Malaysia Standard MSIG. The primary sedimentation tank was designed as a rectangular tank to allow uniform flow distribution, effective solid settling, and ease of operation and maintenance. The tank has a length of 13 meter, width of 7.5 meter, and deep 3 meter, resulting in a surface area of 225 meter cube and a working volume of 675 meters square. This dimension provides sufficient settling area for the removal of settable solid from the influence wastewater. At the design flow rate, the calculation detention time is 1.754 hour, which fall within the recommended range for primary sedimentation tank. This detention tank is adequate to allow suspended solid to settle while minimizing the risk of septic condition. The horizontal velocity of 4.79 mm per second is relatively low, which is desirable as it promotes effective sedimentation by preventing resuspension of settled solid and ensure laminar flow condition with the tank. For effluent withdrawal, a weir system consists of 9 parallel wells, each 7.5 meter long, was provided, giving a total weir length of 97.5 meter. This configuration ensures uniform flow distribution across the tank width and minimize short-circuiting effect. The calculated weir loading rate of 138 meters square per md is within acceptable design limit, indicating that the effluent flow is evenly distributed and reducing the potential for hydraulic events that could affect settling efficiency. Overall, the primary sedimentation tank design meet hydraulic and operational criteria, providing effective removal and settable solid and contributing to improve performance of the downstream biological treatment process. Based on the design result, a rectangular balancing tank was selected to ensure effective flow equalization and stabilize hydraulic loading to downstream treatment unit. The tank was designed with a length of 24 meter, width of 8 meter, and water depth of 3 meter, giving a calculated surface area of 193.9 meters square and a total working volume of 580.54. This volume is adequate to accommodate variation in influence, flow, and load at a peak flow rate of 9288.61 meters square per day, which is equivalent to 387.03 meters square per hour. The tank provides a detention time of 1.5 hours. This detention time is within the recommended range for balancing tank, allowing sufficient time to deepen peak flow flocculation without causing excessive solid settling. To prevent sedimentation, ensure homogeneous mixing, continuous aeration and mixing were provided. The air requirement of 580.54 meters square per hour ensure adequate circulation within the tank. Freeboard of 0.30 to 0.50 m was included to accommodate water level flux, while the calculated mixing power of 2.90 kilowatt is sufficient to maintain solid in suspension and avoid dead zone. Consequently, the total wall height was designed between 3.30 and 3.50 meter. The balancing tanks designed effectively achieve flow equalization, improve operational stability of downstream unit, and enhance the overall performance of the wastewater treatment.
Today I will give a brief overview of the conventional aeration tank used in our watershed treatment plant, and the system is designed to handle a design flow of the approximately 90,200 16.761 meter cubic per day with a hydraulic retention time of 8 hours to ensure effective biological treatment. The total value of each tank is around 431 cubic meter, and there are two tanks arranged to a parallel. Each tank has a length of the 14.98 meter, width of the 734 meter, and the depth of the 4 meter. At the bottom of the tank, there are the aeration first provide oxygen to the water, allowing microorganisms to break down organic matter efficiently. The cast-style illustration show a 3D view of the two tanks, including the inlet and outlet, and aeration system at the bottom. Overall, the design ensures that the tank can provide sufficient oxygen and detention time, supporting effective anaerobic treatment before the water move to the next stage. I will give an overview of the secondary treatment tank designed for our wastewater treatment plant. The system is designed to handle a peak flow of approximately 90,200 at 16.761 meter cubic per day. To ensure effective biological treatment, each tank provides a detention time of 2 hours, and the total volume required is about 387 cubic meter. which is a discrete among 3 parameter tank, each with a volume of a upright 749.865 meter cubic. Each tank is divided into sections. The first block is the active treatment zone with a depth of 3 meter, length of 18.15 meter, and with a wide width of 6.05 meter. The second block is the sludge collection zone, which is 1 meter deep, 18.5 meter long, and 2.59 meter wide. And the cut schematic show both of a top view and side view, illustrating the layout and structure of the 3 tanks. Wastewater enter the active zone where the microorganism break down organic matter, and the sludge settle in the secondary zone before the treat to water exit. Overall, this design ensures that the tank can handle peak flow efficiently, support effective treatment, and prepare the water for the further processing.
The screening unit is designed to handle a daily flow of 9,286.761 meter cubic per day. The screen opening size is 25 mm with a blade thickness of 10 mm and a total of 6 blades of installed. The channel dimension are 0.2 meter with width and 0.85 meter depth. Over a 7 days period, the estimated volume of screening is 65,007.533 meter cubic. Flow velocity will be determined based on channel design and operational requirement. For the grid chamber unit, the design flow rate is 9,266.761 meter per cubic per day. Retention time of 118 seconds is applied to allow optional grid settling. The flow velocity within the chamber is 0.02687 meter per second, which is suitable to prevent light organic matter from settling. The chamber dimensions are 5 meter in length, 2 meter in width, and 1 meter in depth. The surface loading rate achieved is 928.6761, indicating efficient removal of sand and heavy particle prior to further treatment. The conclusion is a wastewater treatment plant was designed for a residential area with a population equivalent of 11,487 based on projected domestic wastewater generation. The design fully complies with MSIG volume for 2009 and relevant Malaysian standard to Asia regulatory acceptance. Key unit operations such as the sewer system, primary treatment, and secondary treatment were selected based on efficiency and sustainability for the given PE. All design calculates were systematically carried out using Microsoft Excel to ensure accuracy and consistency. The overall plan, layout, and treatment unit were clearly illustrated using AutoCAD for proper visualization and planning. Overall, the proposed design offers an efficient, sustainable, and particularly solution for managing domestic wastewater in the study area. Besides that, this project also creates several entrepreneurial opportunities. This project opened up several business opportunities in wastewater treatment. One of them is providing consultancy service to housing developers, especially in design wastewater treatment plant, WWTP, and making sure that follow environmental regulation. Next, modular WWTP system can be developed for small communities and rural areas. These systems are cheaper, flexible, and easier to install, making them suitable for areas with limited facility. There is also an opportunity in resources recovery, where sludge from the treatment process can be turned into useful products such as biofertilizer or biogas. This helps reduce waste and support sustainable practice. In addition, operation and maintenance
service can be offered to ensure the WWTP runs efficiently and meets effluent standards. Lastly, training and short courses can be conducted to increase awareness and basic knowledge about proper wastewater management. Lastly, about reference. For reference number 1, the Malaysian Sewerage Industry Guideline Volume 4, 2009 was used as the main guideline for unit operation design. Next, for the reference number 2, the wastewater engineering textbook was used to support calculation method and design concept. And for reference number 3, Google Earth was used to estimate the site area and sustainability of the treatment plant location. And thank you.